那么今天呢，会议最后的一场演讲是来自英特尔的首席技术工程师 Kevin Aliero 分享的调试线程和内存错误，有请。
Today's presentation is entitled Find and Squash Races, Deadlocks, and Memory Bugs with Intel Inspector. I'll be covering an overview of Inspector, which is a memory and threading debugger. Let's get started. In today's agenda, I'll be covering an overview of Inspector. I'll also be covering a deep dive into some of the Inspector features, and I'll finally wrap up with a summary. Before we get started on Inspector, I'd like to go over a few of the other tools which are part of Intel One API. On the top part of the screen, you have our cluster tools. So if you're using MPI programs, we have some analyzers such as Intel Trace Analyzer and Collector and Intel Application Performance Snapshot. These can let you tune your MPI programs. In the middle part of the screen, we have our tools that can analyze single node optimizations. So if you try to get effective threading, or if you're trying to vectorize your program or trying to get more memory bandwidth, tools like Intel vTune Profiler and Intel Advisor can be very helpful for that type of optimization. Where Inspector fits in is Inspector is not a performance optimization tool. Inspector is a correctness tool. So Inspector lets you find errors in your memory and threading issues in your program. So I mentioned the term correctness tool. So as applications keep growing and they keep getting more complex, a lot of projects are finding that rather than working on new features, they're spending most of their time just working on defects in their programs. So a correctness tool basically fits into the development lifecycle and lets you find the errors as you're developing your program rather than after the program has shipped. So finding errors earlier is always better. It basically reduces the time, effort, and the cost to repair your application. So as I mentioned, Inspector is a memory and threading debugger. It's a correctness tool that lets you find errors earlier in the life cycle. These problems can be very difficult to diagnose. Problems like races and deadlocks are not easily reproduced, and memory errors can be very hard to find without an analysis tool. Inspector also integrates with your debugger. So even if the issue is not apparent by looking at the diagnostic, the debugger integration lets you root cause that problem easily. So what are some of the issues that Inspector can find? So on the memory side, it can find things like memory leaks, invalid accesses, uninitialized accesses. It can find, for threading problems, it can find data races, it can find deadlocks. If you're using some of Intel's latest memory technology, it can find issues with your persistent memory programs. Inspector works with C, C++, C#, Fortran, but it does work at the binary level. So really, it can find issues in any application. Inspector is simple, reliable, and accurate. It does not require any special recompiles, and it works with any compiler. It's a dynamic analysis tool. It can also be used to analyze your applications that do include third-party libraries. So it doesn't require a source. It includes a user interface, and it also integrates with your debugger. Inspector also has a command line version, which is excellent for automated regression analysis. So how does Inspector work? So Inspector uses dynamic instrumentation using a tool called PIN. Using PIN, we can track all memory allocation and threading APIs in your program. And it does this by using binary instrumentation. So by using PIN, recompilation and source modification is not necessary. So the methodology that we recommend is basically first to set up your project. Then you need to configure your analysis and tell Inspector what type of analysis you would like to do. So finally, you would launch your application using Inspector, and Inspector would present you with a list of problems. So then you would look at each problem and then try to determine what the root cause of each problem was. And then finally, you would fix your problem and then rebuild your application. And basically, this is meant to be systematic, and you'd incrementally go through your problems and finally come up with an application that was much more reliable. So just to review, Inspector uses dynamic instrumentation, does not require special builds, can use any compiler, and sources are not required. It can find memory errors and threading errors. So some of the memory problems that we can find, let's kind of do a deep dive into those right now. First, it can find memory leaks. So a memory leak is when a block of memory is allocated, but is never deallocated. And also, not only is it not deallocated, it is no longer reachable. So there is no longer a pointer back to that problem, back to that memory. So basically, it's impossible to free. The second set of problems is similar to a memory leak, but in this case, a block of memory is allocated. It's never deallocated, but it is still reachable. So there is a pointer to that memory, and you could conceivably eventually free that memory. Third problem is memory growth. So in this case, a block of memory is allocated, but is not deallocated with any specific section of your program. Another problem is uninitialized memory access. In this case here, we have our variable A, which we're declaring, but we're never initializing. The second problem is invalid memory access. So in this case here, we're trying to reference memory that is not legal memory. In this case, we're allocating some memory, but then we're freeing it. But then after we're freeing the memory, we're trying to use that memory, which is illegal. Next problem, kernel resource leak. And finally, GDI resource leak. So to briefly cover some of the threading problems that we can analyze, we can monitor the thread and sync APIs. So if you're trying to access memory between threads, we make sure that you're doing that in a way that does not cause a data race. So again, we can use C, C++, and Fortran. We can also use C#, and a code path must be executed in order to be analyzed. So I've mentioned data races several times. Let's just kind of go over what exactly is a data race. In this example, we have two threads, thread 1 and thread 2. So in the first case, thread 1 is doing a read, it's doing an increment, and then it's doing a write. Thread 2 then steps in and does a read, an increment, and a write. So eventually, we come up with the final value of 2. In our incorrect case, we have thread 1 and thread 2. Thread 1 is first doing the read, and then immediately thread 2 is doing the read. And then we go back to thread 1, which does its increment, and thread 2 does its increment. Finally, thread 1 does a write, and thread 2 does a write. So we come up with the eventual value of 1. As you can see, depending upon the order that we process our threads, we come up with a different value. These problems are very, very difficult to reproduce, and tools like Inspector can make finding these issues much, much easier. So let's cover some of the workflow in Inspector. So one of the first things you need to do is configure your analysis type. In our case, we have threading error analysis or memory error analysis. So in this case, I'm going to select threading error analysis. Once we select our analysis type, we go to the middle part of the screen, and we're basically selecting the level of thoroughness that we'd like to do. Depending upon the level, it has some slowdown that you can expect. So if you select a level 1 analysis for threading analysis, you could conceivably slow down your program by a factor of 10 to 40 times. By doing a level 2, you could conceivably slow it down by 20 to 80 times. And finally, for level 3, you could slow it down by a factor of 40 to 160 times. And by doing our analysis under Inspector, it does have some additional memory overhead. So the reason why I wanted to mention these levels is the recommendation would be to start at the lowest level, so that has the least amount of instrumentation and the least amount of slowdown, and then eventually slowly move up the levels as you want to uncover more and more issues. That's just a recommendation. Finally, once you've selected the level, you would click on Start. Inspector would launch your application and basically start collecting issues. So once your application has executed, Inspector would present you with a list of problems. So what Inspector does is it basically aggregates all the diagnostics and presents a list of problems to you. So for example, if you were to select threading error analysis, there could be hundreds of diagnostics which are of the form of a data race. But each one of those different diagnostics could be associated with a single data structure. So what Inspector does is it notices all those issues that it found are actually coming from one problem. These problems just basically give you an easier way to associate that problem, and basically makes it easier for you to fix it. In this example that I'm showing here, the first problem is a mismatched allocation and deallocation. If, for example, you were allocating that memory inside of a loop, and the loop was looping 100 times, then there would only be one problem. There wouldn't be 100 problems. So it just makes it easier for you to navigate all these issues inside of your program. By selecting a problem, it presents you with a code snippet for that problem. In this case, we're doing an allocation using new, but we're trying to deallocate it using free. Inspector is basically telling us that this is an issue. Inspector also gives you a way to filter problems. You can basically filter by the type of error, the severity of the error, the source of the program. We also present you with the call stacks of the program. Inspector also has a concept known as state, which I'll be covering in a slide coming up. By double-clicking on the source, you basically bring up the source window. And we also present you with the call stack for the allocation and the deallocation. I've mentioned we also support Fortran. So Fortran is a fully supported language inside of Inspector. So I've mentioned the column state inside of Inspector. I'd like to cover exactly what we mean by state. So Inspector includes an easy way to manage your problems. So basically, you can see when you have new problems and you have regressions inside of your program. When you first run your application through Inspector, your state will be new, meaning it was first detected during this run. If you run Inspector again, then Inspector would basically notice that this problem is no longer new. It's in a not fixed state, meaning it was seen previously before this run. So once you start doing root causes on your problems, you basically can start using the GUI to basically set whether a problem is not a problem, whether you confirm it is a problem, or whether the problem is now fixed. Once you set a problem as fixed, if you were to run inspector again and that issue is still there, inspector would tell you that this is now a regression. Inspector has a really nice way of filtering problems. If you're dealing with a large application, you can come up with hundreds of errors. Inspector has a really nice way of basically focusing in on the errors that you're interested in. If, for example, you're working in a group and you only wanted to focus on a particular source file, you could basically select that source file and say, I only want to see errors that are coming from this source file. One of the recommendations we have is for you to set the filter to be not investigated. So basically that way you would only be presented with issues that you haven't investigated yet. But you could also set it to be investigated. It just depends on the process your group is following. So Inspector has a really nice way to diagnose memory growth. So on the right-hand side, we have a chart of the memory usage over time. The list of problems we actually have memory growth. So what you can do is you basically can set points in your program and measure how much memory is growing between point A and point B. And by selecting that problem, you can actually see what allocation is causing the memory to grow. A lot of times it's not easy to see. It's not easy to determine why am I using so much memory in my application. It's usually because you're not freeing it when you probably should be freeing it. Inspector has a fully functional command line. It's often used to automate regression analysis. So what you could do is create scripts using the inspector command line, and usually create a baseline of errors that you expect to be coming from your program. And then you could set your scripts up to be run every night. And then if new issues creep into your program or you start seeing regressions, Inspector can flag those issues automatically. So you can collect you can collect issues, but you can also report on the issues using the command line as well. Inspector also has a way to compare results. So if you were to use Inspector to do regression analysis, what you could do is create a baseline and then run Inspector again and be able to compare what's changed between result 1 and result 2. It's just a nice way to find those issues easily by comparing the results. One of the nicest features of Inspector is our interactive debugging support. So the first way is basically to analyze without using the debugger. The second way is to enable the debugger when a problem is detected. So if a diagnostic occurs, then Inspector would bring up the debugger and you would actually see what was the context for this error to occur. And the third way, finally, is to start analysis when a debug breakpoint is hit. But my favorite way to use the debugger is basically to run my application using Inspector, select the diagnostic and say, debug this problem. So how that works is basically, if you say debug this problem, Inspector would run your application again and basically bring you to the exact location where that error occurred. This provides a really nice way to root cause your problems when it's not apparent what was causing them. Some of the other features are the ability to suppress errors. So I've mentioned that you could basically use the Inspector problem management to basically say when a problem is not really a problem. So Inspector has an editor that lets you create these suppressions. So once you know that something is not an error, you could basically suppress that error. So So it's not going to occur every time that you run your application. Another feature is a way to limit the scope of your analysis. In some of the inspector analyses, it could really slow down your application by quite a lot. So sometimes, if you're not interested in a particular part of your application, you could basically tell inspector, I want you to stop collecting here and start recollecting here. That's just a way of limiting how much your application is slowing down. So at a glance, we've talked about basically viewing the context of a problem and basically reducing those sightings to one error. We've talked about being able to suppress, being able to filter, using inspectors workflow management. We also integrate inside of Visual Studio. We have a fully functional command line to automate tests. You can visualize your program along the timeline. You can see that memory growth. And we also have a really nice debugger integration. Changing gears here really quick, I want to talk about one of the newest features of Inspector, known as Persistence Inspector. One of the problems with persistent memory programming is a memory store does not become persistent immediately. The data only is persistent after it is flushed out of cache. So the solution here is not to just add these cache flushes. You really only want to add those flushes when they're necessary, because if you do excessive cache flushes, then you will hurt your performance. So Inspector is a tool that lets you find these persistent memory errors. So as an overview, what is the Persistence Inspector tool? Basically, it's a runtime tool that can detect these programming errors in persistent memory programs. In addition to finding these cache flush misses, it can also find a redundant cache flush or a redundant memory fence. It could find out-of-order persistent memory stores. And also, if you're using the PMDK, it can find incorrect logging inside of the PMDK. And you can visualize all of these errors using the Inspector GUI. So as a summary, I wanted to give a call to action. To really get the most out of your hardware, you really need to modernize your code using vectorization and threading. Taking the methodical approach, as I've outlined in this presentation, can really make programs much more reliable and find those really tough to find issues. Thank you for your time.